Hey. So last time we talked about NP, and one of the things we talked about is this definition and lemma shown on the screen now for deciding when a language is in NP. You define a verifier is a deterministic Turing machine. So to show that something is in NP, we're going to be like writing flowcharts and saying, here's how the machine works. And then we show that a language is in NP by producing this machine and showing that its verifier that we've just drawn a flowchart of runs in polynomial time. Okay, so here we go. The verifier halts on all inputs sigma comma omega, lost my mouse, where the heck, there I go, sigma comma omega, it halts on all inputs in time polynomial length sigma, and is such that sigma is an L exactly if and only if there's a witness omega. And we're thinking of the witness omega as being the hint provided by the daemon here. Whoops, come on, the daemon here. Okay, so you can think of the witness as being the guess, or the suggestion, or the hint, or the certificate that the daemon has given you, and you only have to check that one thing. If that one thing checks out, if you can verify it with the verifier, then you accept sigma. Okay. All right. Whoops. We did an example last time. Satisfiability is an NP, and satisfiability is a perfect case because we think about if you want to show that a Boolean expression is satisfiable, what you want to do is go through the truth table. So you say, well, the problem with the truth table is not any particular line, just that there's a whole lot of them. There's exponentially many lines, and so the issue is not any one line, the issue is sort of all the lines. So if you got a hint, if somebody told you which line to check, you could check it very quickly. So the verifier just simply goes through here. The verifier just simply goes through and verifies that single line. So the verifier takes sigma is the Boolean expression, and omega is the hint. Okay, so somebody gives you, somehow they say try line 4108, and then you check that. You can check that very quickly, and you say, okay, 4108 comes out with a T on the far end, so we've decided that sigma is indeed satisfiable. So a problem is in NP if there's a fast way to check. Not necessarily a fast way to find, that we'll talk about this more later, but a fast way to check that it's in the language. Whoops. There we go. Okay, so I want to talk about the verifier definition a bit and the lemma that makes the definition work. So the first thing when you think about the definition is that it says there exists a witness omega. It doesn't say where the witness comes from. So a person who's got a computational mindset, that is, say, a person who's in this class, will say, but wait, how do I compute omega? I mean, how do I calculate omega? That's the whole nut. If I could calculate that, well, I wouldn't be doing all this. Yes. That's a very sensible thing to say. But the definition, the way it reads, it's not the point to find omega. Instead, the point is that you could verify omega if you were given it or guessed it. Or maybe unboundedly branched and one of the branches finds it. So we don't find the omegas. We don't compute the omegas. I understand why a person reacts like, how am I going to compute the omega? I understand that. We don't compute the omega. The point of the definition is not to find omega. Instead, the point of the definition is to use it once you have it. Okay. Second, the flip side of the definition. If sigma is not in L, the definition doesn't ask you to give a witness to that. Instead, if sigma is not an L, what the definition asks is that from among all possible witnesses, there's none so that the verifier accepts the inputs. From among all possible witnesses. So in the first of the two bullet points, what you see is that you're looking for there exists a witness, And in the second, what you're looking for is from all possible witnesses, none works. So there's an asymmetry between the two. That's absolutely right. And the third comment relates to that asymmetry. So it's going to be two different paragraphs that try to make the same point. First paragraph. Imagine that the demon gives you a big pile of papers. I don't have a big pile of papers around here. Imagine that the demon gives you a big pile of papers and claims they contain an unbeatable strategy for chess. Well, that'd be great. Now, it's a demon, so you can't believe him when he gives you a pile of papers you want to verify. But the problem is that verifying this big pile of papers requires that you look at the first move you're told to make and check out every response to that move and the responses to the responses and the responses to those responses. And it sure seems like there's a heck of a lot of branching here. So maybe a person says, well, this is a kind of branching problem that we've been thinking about. Fair enough, except that to show that your strategy is indeed unbeatable, you can't just come up with one good branch. You have to show that every branch you track, the response to this move, and then the response to that move, and then the response to every branch that you check, it ends in a win. So you have to show not there's one good branch, but rather that all branches are bad, or all branches are a win for the first player, or whatever it is you want to show. So it doesn't seem like a deterministic verifier can do that at polytime. It seems like a deterministic verifier is going to take exponential time to do that. So chess strategy, this problem that I've just posed, is a kind of a complement to the problems that we've been considering. We've been considering a problem like the traveling salesman problem around the lower 48 in the United States, where if you find one, 16,000 kilometers, you can do it this way. If you find one, you're good. That's it. You found it. But with chess strategy, all those branches, every single one has to be checked. So in some sense, chess strategy is a different kind of problem than the kind we've been looking at. It's kind of a complement to the kind we've been looking at. In fact, if somebody wanted to show this isn't a perfect chess strategy, they're only going to find one way to break it. So they're really the kind of problem that we've been thinking about. Another way to express that same sense of the asymmetry here is that imagine that you have a problem L that's in NP, and you want to think about the problem L complement. So, for example, consider satisfiability. A propositional logic expression sigma is satisfiable. Then there's a witness that points to the line of the truth table. But to show that sigma is non-satisfiable, apparently what you have to do is check every single line of the truth table and show that it leads to an F. So to show non-satisfiability, you can't just reach out and grab that one good line. You seem to have to check all of the exponentially many lines. As far as we know today, verifying that a Boolean formula is not satisfiable takes more than polytime. Expressing the same idea, where the complexity class co-NP contains the complements of the languages in NP, we suspect that co-NP and NP are not the same. But just because a language is in NP doesn't mean its complement is in NP. So there's an asymmetry between yeses and nos here. So the lemma explains something about the class NP. While P contains problems where we can find the answer in polytime, what NP contains is those problems whose answers are useful in that we can at least verify them in polytime. So NP is kind of a stretch beyond P. We might not be able to find the answer, but we could verify it in polytime. Okay, and then finally, a maybe more technical point. So the lemma requires that the runtime of the verifier is polynomial in length sigma, not polynomial in the length of the verifier's input, which might be your first guess. What's the problem with polynomial in the length of the input? Well, if we said polynomial in the length of the input, then we could, for example, check the chess strategy just by making the witness be extremely long, exponentially long. And that would give us time, exponentially much time, to check the strategy. Okay, so we don't want that. We want that the answers are checkable in polytime, as we said on the prior slide. So also, a point along the same lines, observe that because the verifier runs in time polynomial in length sigma, for it to accept, it has to be able to get a hint that it can use in time polynomial in length sigma. So there must be an omega that is whose length is at most polynomial in length sigma. Because if the omega was too long, then the verifier couldn't even read it in before the runtime bound expired. Okay? All right, so with that understanding, with that, I hope, increased understanding of verifiers, which often give people trouble, then we want to do an example or two here. Okay, so for example, Hamiltonian path. Hamiltonian path problem is like the Hamiltonian circuit problem, except that instead of requiring that the starting vertex equals the ending one, it inputs two vertices. So you're looking at a graph, all right, and then you're looking at two vertices, v and v hat. And you just want that the path between v and v hat visits every vertex once. Exactly once. Okay, so I want to use the verifier definition and the verifier lemma to prove that, that this problem is in class NP. So I have to produce a verifier v. It has to take in two inputs. The two inputs are going to be a proposed member of L, and also a witness. The witness, perhaps you might think of as the hint that the daemon is going to give you that sigma is actually correct, that sigma is an element of capital L. Okay, so here we go. The verifier V, I keep losing the map. Oh, there it is. The verifier V, it reads in two inputs. It takes the hint. The hint is actually the path that runs from V to V hat. It checks that hint. It reads in the omega, the path from V to V hat, and it checks, is it indeed a path in the graph, capital G? Well, that doesn't take long to check. I mean, certainly polytime in the length of capital G. So then if you check that, if you check that all vertices are visited once and only once, that is indeed a Hamiltonian path, then you can accept, and of course if it fails, then of course you reject. So this is the algorithm, this is the Turing machine, this is the verifier V, clearly deterministic. And we want to check the two possibilities. First, if there is a Hamiltonian path, then there is such an omega. I could give you the Hamiltonian path, and you might say to me, well, where'd you get it from? Well, you know, I have superpowers. I gave you the Hamiltonian path. You can check it quickly. So if there is a Hamiltonian path, if there is, in capital G, if sigma is indeed an element of capital L, then we're good. V accepts. There is such an omega. On the other hand, if sigma has no such Hamiltonian path, then it doesn't matter what hint I give you. It doesn't matter what the daemon pretends to give you as helpful. It's not helpful. There is no such omega. So there's no way for V to accept. You will always end up on the reject branch no matter what omega you get. Again, this asymmetry. If sigma is such that there is a Hamiltonian path, then there is at least one omega. There's a hint a daemon could give you. There is at least one omega that will end you up on the Y branch. On the other hand, if sigma is not in capital L, script L, then it doesn't matter. There's no omega that will work. So there's an asymmetry between the one and the all. If sigma is in capital L, then there is at least one omega. If sigma is not in capital L, then there is no omega. Okay, a couple more problems on this slide here. The vertex-to-vertex path problem, sometimes called path, sometimes called ST-con, all kinds of names you'll find out on the internet. The vertex-to-vertex path problem takes as input a graph and two vertices, and then decides if that triple is in the language by whether there's a path between the vertices in the graph. Okay, very straightforward to state. So I take, for example, a map, and I look at two cities, Cairo and Lagos. And I say, is there a road that leads from Cairo to Lagos? At least one. So I'm claiming this problem is in NP. So for the witness, omega, you could just use the path. The daemon could give you the path, or you could guess it, or you could branch all the possible branches, and one of them will find that there is indeed such a road. We could clearly write a verifier that accepts the triple sigma and the witness omega, and then verifies that the path lies in the graph. And let's see how I do with it. I'm going to sketch this thing, so start. So read in sigma and omega. And then the second thing is just simply check that the path omega leads from the one to the other, from v to v hat. V and v hat are part of sigma. Sigma is a triple. G, v, v hat. So the path omega leads from v to v hat, question mark. I forgot to write the question mark. And you either have a yes or you have a no. So if yes, then you accept. And if no, of course, you fail to accept. And this is a verifier. This is the verifier that we need. Come on. Whoops, there we go. Verifier. It's a verifier that we need, and I need to erase that little scribble that I didn't mean to make there. If you indeed have, in your sigma, if you indeed have a path between the two vertices in the graph, then there is such an omega. I could give you the path, and that would be the witness. If, however, the triple G, v hat does not contain a path from v to v hat inside a capital G, well, then there's no way to end up on the S branch. It doesn't matter what omega you get. You can't end up on the S branch. So that, by definition, means that that the verifier is doing the correct thing. So we're not accepting sigma, omega in that case. So another example, just going to do two more examples here. Another example, linear programming optimizes some objective linear function subject to a list of linear constraints. To make this a language decision problem, we've seen in prior work in this chapter that you can define it as a set of pairs f, c, where f is the linear objective function and c is the set of constraints. And we say that a pair f, c is in this language if there is some set of numbers, we might say integers or rational numbers, or if you don't want to worry about floating points. If there is some set of numbers that satisfies the constraints and that makes f greater than capital B. Okay, now I can write a verifier that will check a pair sigma, omega, where sigma is f, c. All I got to do is, for the hint, for the omega, I'll take the actual tuple of numbers, in this case an n tuple of numbers that works. There might be many tuples of numbers that work. I'll give one. It's easy to check that. So the verifier will have no trouble in polytime verifying that it works. On the other hand, if there is no such tuple, then the verifier can't possibly verify what I've handed in. Okay, so the verifier is doing the right thing here. So we conclude that linear programming, the collection of problems here, L sub B, that linear programming is indeed a member of NP. One more, three coloring. Three coloring takes a graph as input and decides if it can be colored with at most three colors. So sigma is going to be a graph, G. I'm going to propose to write a verifier that takes in sigma, omega, and then either accepts or rejects. Well, what do you think we're going to use for omega? I think I'm going to use a three color. If the graph has a three color, then there is such an omega. But if sigma happens to not be three colorable, then it doesn't matter what omega I give you. It can't possibly, the verifier that I just sketched out loud can't possibly work. Okay, so in each of these three cases, and the prior case too, in each of these three cases, I wrote a deterministic Turing machine. I wrote a flowchart. It takes in sigma comma omega. It either results in accepting sigma comma omega or failing to accept sigma comma omega, rejecting. It interprets omega as a hint that enables it to verify that sigma is indeed in the language. And we don't have to say where omega came from. We only have to say there exists such an omega if sigma is indeed in L, or there does not exist such an omega if sigma is not in L. Okay. Okay, I'm going to give the statement of the lemma one more time and end with the proof of the lemma. So the statement of the lemma is what we've just been going over, that a language is an NP if and only if it has a polytime verifier, a deterministic Turing machine that runs in time polynomial in length sigma. That is, L is in NP if and only if there's a polynomial P and a deterministic Turing machine V. Halts on all inputs sigma comma omega in time polynomial in the length of sigma, and is such that sigma is in L exactly when there's a witness, where V accepts sigma comma omega. Okay, sigma is in L if and only if there is a witness. Okay, that's what exactly when means, if and only if. Okay, so we want to prove this. So we're going to first suppose that the language is in NP, so that L is accepted by a non-deterministic Turing machine, and then later we're going to say suppose that we have a language that works with the verifier. Okay. So first we suppose that the language is accepted by a non-deterministic Turing machine. We got to construct a verifier that works. Okay. So the idea is that we think about what the non-deterministic machine is doing. So I'm going to sketch out here what the non-deterministic machine is doing, and I always draw the same sketch. It's some kind of computation tree. So I don't know, I can't remember the computation tree that I drew earlier. Maybe it does something like so. And so I have a couple of finite branches here. Maybe that one's a little longer. And maybe I have an infinite branch, and this branch just keeps going and going and going. Maybe, I don't know. And then maybe also, maybe there's another branch here. And this one at the end results in accepting. Okay. Now, I think that I could give you a hint about what to do here that would result in a quickly checkable here I gotta change my color here. Quickly checkable. Quickly, the verifier could quickly check it. Okay, trying to think and click at the same time. So maybe I'll give you a hint that says, let's see, there are 3 branches here, so I want you to take the third one. And then there are 2 branches here, so I want you to take the second one. And there's only one thing to do here, so I want you to do the one thing. And I'll call that the hint. Okay. Now, if I gave you the hint, 3, 2, 1, then you avoid all the exponentiality of branch, 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 branch. You only just have to follow the branches where they go. I think you can do that in polytime. So from the non-deterministic Turing machine, there is a hint. Never mind how you would find it. There is a hint that will result in you being able to, in polytime, check. So that's what we need. We need for there to be a flowchart. The flowchart is going to say, start, read in sigma comma omega. The next box will say, follow the hint omega. In this case, it says 3, 2, 1. Follow the branching in the hint omega and verify that you end up at an accepting node. Yes or no? Okay, well, clearly you can do that in polytime. So I think we're good there. What about the other way? The other way is that you suppose that a language is accepted by a verifier v hat, and that verifier, of course, runs in polytime. And I keep losing the mouse. There we go. Verifier, of course, runs in polytime, and I want to construct a non-deterministic machine that in polytime accepts an input string if and only if tau is in L. Okay, and the key here, the main idea that we need for this half of the proof is that p hat, the thing we're constructing, is allowed to be non-deterministic. That's the whole point. So given a candidate tau for membership in the language, what you do is you have p hat guess at a witness. You have p hat non-deterministically produce a witness, omega hat, of length less than polynomial length of tau. Then just simply have p hat run tau comma omega hat through v hat, and if the verifier accepts the input, then p hat will also accept tau. If the verifier does not accept the input, then p hat rejects tau. So p hat is non-deterministic if it's allowed to make a guess at the witness omega, or it's allowed, you can imagine a daemon. So we can then just run it through the verifier and check the guess. Does there exist a guess that will work? That's the thing. Does there exist a guess that will work? Not how do I find it? Does there exist a guess that will work? That's the question we have to answer. Okay, so last paragraph here. So we have to check that p hat accepts tau if and only if tau is a member of the language. A non-deterministic machine accepts a string if there exists a branch that accepts the string. It rejects the string if every branch rejects it. Suppose first that tau is a member of the language. Because v hat's a verifier, in this case there exists a witness. Never mind how you find it. There exists a witness that will result in v hat accepting the input tau comma omega hat. So there's a way for the prior paragraph to result in the acceptance of tau. There exists a witness that would work. That's all we need. That's all the definition calls for. Conversely, suppose that tau is not an L. By the definition of a verifier, no witness omega hat will result in acceptance, and so p hat rejects tau. Okay, so what strikes a person as difficult or oddball about this is that you say up here, have p hat non-deterministically produce the witness. And you're like, wait, you're just pulling that out of the air? Yeah, that's how non-deterministic machines work. A non-deterministic machine is allowed to guess the answer. And you say, well, how is a machine supposed to guess? And the answer is that the lemma that we are proving right now, not a bad job, the lemma that we are proving right now says that there is a link between non-deterministic machines and deterministic machines. And that is that if the non-deterministic machine accepts a string, if and only if the non-deterministic machine accepts a string, then the deterministic verifier will work. So there's a link between the two. Okay? Okay. Kind of a tough section. It's a section that gives people a certain amount of trouble. The key here is to do enough homework problems. Key here is to do enough homework problems that you feel that you've got the idea of what the hint is about. Okay, very good then. Thanks.